Assalamu alaikum everybody. Welcome to our second lecture, which is on asymptotic notations. If you recall, in the last lecture I showed you a few examples of how to derive the running time function Tn of an algorithm. Now, after obtaining the running time function, the next stage in the process of analyzing the algorithm is to actually classify it. And we have a number of notations that we use to classify algorithms. And these are what are called asymptotic notations. So this is what this lecture is about. These are the topics. First, we explain what is this asymptotic notation. And then there are different types of notations. So we're going to take them one by one, starting from the one we saw briefly towards the end of the last lecture, which is called theta notation, also called Big-Theta. Then we look at big O. Big O usually gives you the asymptotic upper bound, whereas the theta gives you actually a more tighter bound, so it's called tight bound. Then we look at big omega. So this is the third main notation. So these are the three main notations actually: theta, big O, and big omega. But there are a few others. But before we look at them, we look at the relationships between these three main ones: theta or big theta, big O, and big omega. Why are we calling them big? Because actually there are other two notations which are called little o and little omega. So this gives us five notations that are used to classify the running time function of an algorithm. So we're going to take several examples to demonstrate these different notations. In the last part, we will look at the comparison of some common functions. And as usual, we will end up with a set of exercises which I would encourage you to try and solve. Okay, so what is asymptotic notation? Asymptotic notation is the formal notation for classifying the running time, computational cost, or complexity of running time functions. So these are all similar terms that are actually used to mean the same thing. Sometimes we call it running time function. Sometimes we call it computational cost. Or sometimes we simply call it complexity function. They all actually mean the same thing. So asymptotic notation gives us a formal way of classifying these different running time functions. Its objective is to classify the runtime functions according to their order of growth as input size increases. Okay, because as we mentioned towards the end of the last lecture, it is really the order of growth of a function that determines its running time or its efficiency. So instead of looking at individual functions, we would like to group them and say all of these functions, they belong to one class, and that classification is based on the order of growth. Yeah, it focuses on the important term of the runtime function. It ignores the actual and abstract statement costs. It also ignores the lower order terms. So we are only concerned with the term that has the highest degree in terms of the input size n. For example, it allows both the following functions to be classified as n cubed. So either big O of n cubed or theta of n cubed or big omega of n cubed, as we shall see. These are the two functions I'm talking about. So here we have 10n cubed plus 5n squared plus 17. And the second one is 2n cubed plus 3n plus 7. So we said we will concentrate on the term that has the highest degree. In both of these cases, the n cubed is the highest degree. So we're going to ignore the terms with n squared or the constant term or the term with just n. Just concentrate on the term with the highest degree. Both the two functions, the highest degree is n cubed, and we also ignore the constant coefficient for the term, so it's just n cubed. Also, this function is also n cubed. So let's start with big theta. What is big theta? This is the formal definition. It says let fn and gn be two non-negative functions of non-negative arguments. So what do we mean by non-negative functions? If I can just draw a graph like this. So your functions that its values lies in this quadrant, not this side and not anywhere below, okay, is considered to be a non-negative function. As you know, the y is positive this way and it is negative if you go down. So we want the function to go positive. So this is when the function itself is non-negative, but also the argument n is also non-negative, say non-negative arguments. So again, we are concerned with this side of the n, not the other side. Okay, so this is what we mean. So if we have two such functions, then fn, the function fn, is said to be big theta of gn, the other function, if there exist positive constants c1 and c2 and another constant n0, which must be greater or equal to 0. So c1 and c2 are strictly positive. 0 is not allowed, and of course negative numbers are not allowed. But n0 can be 0, but not negative. So if we can find these three constants, c1, c2, and n0, such that the function fn is between c1 times gn and c2 times gn for all values of n greater than the n0. Okay, if we can find such c1 and c2, then we say that fn is theta of gn. In other words, if you like, gn is actually a set or a class, and we are trying to say that this fn belongs to that class. Okay, yeah, so this is another way to look at it. The theta of gn is actually a set of functions for which we can always get the three constants, c1, c2, both of them positive, and n0, which must be greater or equal to 0, such that Fn is greater or equal to C1 times Gn, but less than or equal to C2 times Gn. And this is for all n values. N is the argument, if you remember. So for all values of n that are greater than n naught. Still, we can put this another way. What this means is theta of Gn is a class of all functions Fn that grow at the same rate as Gn. So essentially we are saying Fn grows at the same rate, exactly the same rate as Gn. Now I know this sounds all too mathematical. They say a picture is worth 1,000 words. So let's try to demonstrate this example using a graph. So here we have our function Fn. So what we are saying is Fn will be considered to be theta of Gn. Notice there is a misnomer here actually, because Fn is one function and theta of Gn is a set of functions, and we are trying to equate them. You cannot equate a single value with a set of value, but actually that is the convention. When we do this, when we say Fn is equal to theta of Gn, all we are saying actually is that Fn belongs to the set theta of Gn. Yeah, but this is a common practice to use equal to say Fn is theta of Gn. It will sound like we are saying they are equal. No, they are not equal. We are just saying that Fn belongs to this class. So the theta of Gn is a class. Fn belongs to that class. Okay. So looking at this graph, if this is our function, then we are saying it is going to be theta of Gn if we can find constants C1 and C2 such that Fn will always lie between C1 times Gn and C2 times Gn. You can see that Fn is between the two, right? Now, but not for all values of n. Fn may be bigger or even smaller than both for small values of n until we reach n naught. So, but here after n naught, the inequalities, the two inequalities should always hold. Fn should be between C1 times Gn, so this is C1 Gn, this is one function, and this is C2 Gn. It's the same function, we're just multiplying it by a constant or by two constants. So if this relationship is always true, that Fn is bounded between these two functions for these values of n, okay, from n naught here forward until infinity, the Fn is always going to be between. Okay, it doesn't matter if Fn is below both of them, as you can see here, or greater than both of them initially, at least until n naught. So we will be able to find some n naught, after which Fn is always going to be between these two, C1Gn and C2Gn. If that is the case, then we say that Fn is theta of Gn. Okay, so again, looking at it differently, theta of Gn is a set of functions. So all functions here within this yellow portion, where the functions are bounded between C1 and Gn and C2 and Gn, they all belong to the same class. This is what we are saying. So Fn is just one of them. All right. So Fn is theta of Gn if we can find constants C1, C2, which must be positive numbers, and n naught, which can be 0. So n naught can be here actually, but it cannot be negative, such that Fn is going to be between these two functions, C1gn and C2gn. Right, so I hope this explains the definition better. And we're going to take several examples to demonstrate this. Okay, yeah, this is the completion of the definition. It says Fn is theta of Gn if there exists, if we can find a positive number C1, a positive number C2, and a non-negative number n naught, such that for all n greater than n naught, Fn is always going to lie between C1 times Gn and C2 times Gn. This is the definition of theta. Let us take examples to demonstrate this idea. Example number 1 says, show that Fn, which is equal to 10n cubed plus 5n squared plus 17, is theta of n cubed. Now here, let us not forget that this function Fn is the running time of an algorithm, and we saw in the last lecture how to derive this function. It's just that here we are calling it Fn instead of Tn. Alright, so we are saying if an algorithm has a running time function that turns out to be this, then that algorithm can be classified as being theta of n cubed. In other words, it belongs to a class of algorithms whose running time grows at the same rate as n cubed. So n cubed here is our Gn. Now, to show this, we obviously need to satisfy the definition, meaning we have to find those three constants: C1 strictly positive, C2 strictly positive, and n naught non-negative, such that Fn will lie between C1n cubed and C2n cubed for all n greater than n naught. If we can find these three constants, then by definition we are able to show that Fn belongs to this class, or Fn is theta of n cubed. So here is how we do it. Usually C1 is much easier to find because if you look at this function, 10n cubed plus 5n squared plus 17. Suppose we ignore the last two terms, 5n squared plus 17. Then obviously 10n cubed alone will be smaller than if we add to it 5n squared plus 17. Okay, so therefore we can say 10n cubed is less than or equal to 10n cubed plus 5n squared plus 17. Why are we putting it in this form? Because then it will allow us to find our C1. Okay, because remember the definition says some constant C1 times n cubed is less than or equal to Fn. Well, it means we are already able to find C1, because definitely 10n cubed will be less than the function itself without removing 5n squared plus 17. Alright, so what about C2? How do we find it? To find C2, what we normally do is we upgrade the other terms. Let them also be as big as n cubed, so that we will be able to factor the n cubed out, and we will end up with one constant, and that constant will be our C2. Alright, so what we are saying here is our function 10n cubed plus 5n squared plus 17 definitely will be less than if we upgrade 5n squared to be 5n cubed as well, and 17 to also be 17n cubed. Okay, if you do that, then you can factor out the n cubed, and you will have 10 plus 5 plus 17, which is going to be 32. And this obviously will be true for all n greater or equal to 1. Notice that it may not be equal to true for 0, because if n is 0, then here the function will reduce to 17. On the other side, however, we're going to have 0, because we have 32 times 0, which is 0. So obviously you cannot say 17 is less than 0. Alright, so we have to be careful to find the correct value of n for which the two inequalities will be true. In this case, the inequality will be true as long as n is not 0. Anything greater than or equal to 1 will be fine. Okay, so therefore we can simply say that if we take C1 to be 10, C2 to be 32, and our n naught to be 1, then the function fn will lie between C1n cubed and C2n cubed for all n greater than our n naught, which is 1. For all n greater than 1. And that means we are able to find the three constants, and therefore by definition it means this fn is actually theta of n cubed, and that completes the proof. Let's take another example. Show that fn, which is equal to 10n cubed plus n log n, is theta of n cubed. Alright, so again we follow the same process. To do the proof, we need to find three constants, C1 and C2 both strictly greater than 0, and n naught non-negative, which means it could be 0 greater or equal to 0, such that fn is between C1n cubed and C2n cubed for all n greater than n naught. So as we did in the previous example, C1 is much easier to find. We can just take the first term with the highest degree. It will obviously be less than or equal to the function, because the function will be the same thing plus n log n. So definitely the function will be greater. Okay, how about for C2? How can we find it? Well, we can find it by upgrading this term to be in the form of n cubed. Obviously, n log n is less than n cubed. Okay, in fact, n log n is less than even n squared, because if you remember, log n is less than n. Log n is usually much smaller value than n. For example, if you take 100, log of 100 to base 10 is 2. So the log of a number is usually much smaller, and therefore this n log n will be less than n cubed. So if we replace that by n cubed, we will have 10n cubed plus n cubed. So we can factor out the n cubed, and then we are left with 10 plus 1. So we can add that to have 11 as our C2. Okay, and these two inequalities will be true for all n. In fact, this time we can say greater than 0. Okay, but if it is true for n greater than 1, I mean, if it is true for n greater than 0, definitely it will be true for n greater than 1. So it's okay to leave it as 1. But in this case, because there are no constants, we can say for all n greater or equal to 0. But it doesn't matter we don't have to find the smallest value of n naught. We can take any n naught for which after that both the two inequalities will be true. So therefore we can say that if we take C1 to be 10 and C2 to be 11 and n naught to be 1, then our Fn is going to lie between C1n cubed and C2n cubed for all n greater than our n naught, which is 1, greater or equal to n naught. Alright, and therefore our function Fn is indeed theta of n cubed. We note that this example shows that Fn does not need to be a cubic polynomial for it to be theta of n cubed. Because this function actually is not a cubic polynomial. Polynomial, normally we will have the terms in terms of degrees of n. So maybe n square or n, but not involving another function like log. Okay, so we are saying a function can be theta of n cubed even if it is not a polynomial of highest degree n cubed. This is not a polynomial of n cubed because it involves another function log n. Okay, more example. Show that Fn, which is 5n log n plus 10n, is theta of n log n. So again, to show this, we need to find three constants: C1 greater than 0, C2 greater than 0, and n naught greater or equal to 0, for which these two inequalities are true for all n greater than n naught. So C1 times Gn, so C1 n log n, should be less than or equal to our function Fn, which in turn will be less than or equal to C2 times our Gn, which is n log n. So we do as before. Clearly, if we take only the first term, 5n log n, is going to be less than or equal to the function with the 10n included. Okay, so 5n log n is less than or equal to the function, which is 5n log n plus 10n. So this will allow us to find our C1 as 5. Now to find the C2, again we just need to upgrade this second term to be in the form of n log n. Okay, so instead of n, if we replace it with n log n, obviously n log n is bigger than the n alone. So, but if we do that, it will allow us now to factor out and have one constant. It's going to be 10 plus 5, which is 15 n log n. So we have one constant times our Gn. Okay, and this is true for all n greater or equal to 1. Actually, again, in this case, because there is no constant here, all the terms involve n. We can, if we wish, say that this is true for all n greater or equal to 0. So we can choose n not to be 0 if we wish. But if it is true for 0, it is also true for 1. So therefore, if we take C1 to be 5, and C2 to be 15, and n naught to be 1, then we will be able to satisfy the two inequalities for all values of n that are greater than our n naught, which is equal to 1. That proves the statement that Fn is theta of n log n. So this function grows at the same rate as n log n. That's what we are saying. Always don't lose focus of what we are trying to say. We are saying this function belongs to this class. They grow at the same rate. This is another example. the idea of this example is to show you that the function doesn't have to be polynomial. Actually, it could be any function. So here we have fn equal to 2 plus 1 over n, and we are saying this function is theta of 1. Okay, in other words, it grows constantly. It's constant function. That's what we are saying. Okay, if the g is constant, it means the function is constant in terms of the input size, and it doesn't really depend on the n. Okay, so how we will prove this? The same way. We need to find three constants: c1 greater than 0, c2 greater than 0, and n not greater or equal to 0. That will satisfy both the two inequalities. So c1 times our gn, which is 1, must be less than or equal to fn, and that must be less than or equal to c2 times our gn, which is 1, and this will be true for all n greater than the n naught that we are going to find. Now again here, the left side, in other words, finding c1 is very easy. We just need to take the 2. 2 is going to be less than or equal to the same 2 plus some fraction, as long as n is not negative. Of course, not 0 also, because if it is 0, this fraction is not going to be defined. I mean, this term will be undefined. So as long as n is greater or equal to 1, 2 will be less than 2 plus 1 over n. Even if n is 1 million, we're still going to get some value, 0.000 something. So if we add that to 2, it will definitely be greater or equal to the 2 without that addition. Okay, so that is clear. What about the right hand side? We are saying this is less than or equal to 3. Why is that? Because the biggest value you can get in this fraction, 1 over n, is if n is equal to 1. So that you have 1 over 1, which is 1, and 2 plus 1 will be 3. Okay, any other value bigger than 1 is going to make this to be less than 1. For example, if this is 2, then we have 1 over 2, which is 0.5. So the total will be 2.5. 2.5 definitely is less than or equal to 3, and so on. The bigger the n, the smaller this fraction is going to be. So really, it will never be bigger than 1. So we can say that the function is less than or equal to 3 for all n greater than 1. And therefore, we can say we have found the constants. Just take c1 to be 2, so that you have 2 times the gn. Well, the gn is 1. So c1 times gn will definitely be less than or equal to the function itself, this fn, will be less than or equal to this c2, which is 3, times the gn. Okay, and this is true for all n greater than n naught, where n naught is 1. Okay, so that proves the statement. So we note here that theta of 1 is the class of all functions which are constants. All algorithms whose running time doesn't depend on n, they actually belong to this class. They belong to the class of theta of 1. Another example, show that fn, which is equal to 8n squared minus 4n plus 2, is theta of n squared. Now here you have to be careful. For the first time we are having a negative term, right? So you have to be careful. But in any way, the proof is going to be the same. We still need to find three constants: C1 greater than 0, C2 greater than 0, and n not greater or equal to 0, for which the two inequalities will hold. That C1 times our Gn, which is n squared, should be less than or equal to Fn, which should be less than or equal to C2 times our Gn, and that should be true for all values of n greater than n naught. Now this is where you need to be a bit careful. Because of this negative term, we cannot just say 8n squared alone is less than or equal to the function, because this time we are not adding to n squared. We are not adding to this term 8n squared. We are actually reducing from it by subtracting 4n. So it's not, and please, you have to be very careful. Students make this kind of mistakes. It's very common. They will just say, because the previous example, we always say the first term, 8n squared, is less than or equal to the function itself. 8n squared minus 4n plus 2. Students normally do this, and this is wrong, because you see here we are subtracting from 8n squared, so we cannot get, it's not going to be bigger than if we didn't subtract. So this definitely is wrong. Okay, and you have to be careful about it. So what do we do in that case? Well, here is what we do. We will try to see, suppose this 4n were actually 4n cubed. So if we do the subtraction, what are we going to get? Okay, so of course we're going to get 4n squared. So that is what we should have actually on the left side. So we are saying 4n squared, which is equal to 8n squared minus 4n squared, is definitely less than or equal to 8n squared minus 4n. Because you see here, 4n squared is bigger than 4n. Therefore, if you subtract 4n squared, you're going to get a smaller value than if you subtract only 4n. Okay, and therefore this function is going to be bigger. All right, yeah. So that's how to get the C1. We don't just say the C1 is going to be 8 because of this negative term. All right. So how about the other side? The other side is easy. Just ignore this term we are subtracting, okay, and upgrade the term that is constant. Definitely you will have a term that is bigger. Okay, so 8n squared is definitely bigger than 8n squared minus 4n. Okay, and then 2, or rather 2n squared is definitely going to be bigger than the 2 alone. So if you add these two terms, they will definitely be bigger or equal to our function. So with this you can factor out and this is true for all n greater than 1. Okay, greater or equal to 1. So if you factor out the n squared, you will have 10n squared, and therefore you can say that you have found the three constants. C1 is going to be 4, C2 is going to be 10, and n naught is going to be 1. So therefore, if we take C1 to be 4, C2 to be 10, and n naught to be 1, then we have been able to satisfy the two inequalities for all n greater than n naught, and therefore the statement is true that Fn is theta of n squared. Yet another example. So again, this example is going to demonstrate another issue, which is when you have a fraction with the term that has the highest degree. So it says show that Fn is equal to half n squared minus 3n is also theta of n squared. So as usual, to do that, we need to find the three constants, C1, C2, and n naught, where C1 and C2 are strictly positive, but n naught can be 0 or greater than 0, such that our function half n squared minus 3n is going to lie between C1 n squared and C2 n squared. Alright, now here the right side inequality is easy to show, because definitely half n squared minus 3n is less than or equal to the half n squared alone without subtracting the minus 3n. Alright, here we are subtracting minus 3n, on the right we didn't subtract, so definitely this is going to be bigger. Okay, and this is true for all n greater or equal to 1. Therefore, we can easily find C2 to be half. Now remember, the C2 also C1, they don't have to be whole numbers. All that is required is that they should be greater than 0. Well, half is greater than 0, so we have found C2. So therefore the right inequality will hold if C2 is equal to half and n is greater or equal to 1. What about the left inequality? So this is where we have to be careful actually, because you cannot say, it's not enough to just say 5n squared or half n squared is less than or equal to half n squared minus 3n. It will not be correct actually, because we are subtracting something from half n squared. So the result of that subtraction cannot be greater than just the half n squared itself. So here we have to try and find a suitable value for C1. And in doing so, we must make sure that n naught is 0 is greater or equal to 0. So this is how we do it. We say for the left inequality, if we divide by n squared, what do we have? So we will have just C1 here. We are concerned with this left inequality. C1 n squared is less than or equal to half n squared minus 3n. Okay, this is the inequality we are trying to prove for the values of n greater than some n naught. So we are saying to find the C1, suppose we divide both sides of the inequality by n squared. Okay, so if you divide by n squared here, let me delete the cycle. So if you divide by n square, obviously you have to divide by n square here too, minus 3n over n square. So obviously here n square will cancel n square, and you have just c1. Okay, here n square will cancel out, so you have half. But here n will cancel one of the n's in the n square, so we are left with 3 over n. Okay, so the question is what value of c, or rather what value of n, will allow us to have a c1 that is greater than 0. This is the point. You have to be very careful. It's not any n, because for example, if you take 1, okay, if you take n to be 1, then half minus 3 is going to be negative, and c1 is not allowed to be negative. So this is why we're trying to be careful here. You have to find which value of n will allow you to have a positive c. Okay, so we need to find an n such that c1 is greater or equal to 0. Now we say here, since c1 is 0 if n is 6, you can see clearly if n is 6, then this is going to be half as well. 3 over 6 is half, so half minus half will be 0. So we are saying since c1 will be 0 if n is 6, we must take an n to be at least 7. So take n to be 7. Okay, so if we do that, then we are sure what we will have is going to be positive, because 3 over 7 is going to be less than half. Therefore, half minus that is going to be positive. All right. Yeah, so this is the point. Now, so suppose we say n is 7. All right. So if n is 7, what you will have is half minus 3 over 7. Obviously, the LCM is 14. Okay, and we will have 2 into 14, 7 times, minus 7 into 14 2 times 3, which will be 6. So you're going to have 1 over 14. Okay, so in that case, c1 will be less than or equal to 1 over 14. So we can take c1 to be 1 over 14, and it is a positive term, and it will satisfy the inequality. All right, so that's what we are saying here, that we can take c1 to be 1 over 14, which is greater than 0, and therefore we are able to satisfy the two inequalities now. c1 is what we have just found, is going to be 1 over 14. c2, we found it already to be half. All right, c2 is half. The issue now is n naught. N naught can be true in the first case when n is 1, and in the second case when n is 7. So we cannot take the 1, we have to take the 7. Okay, if it is true for 7, definitely it is true for 1, but not the other way around. This is the point. So these are the three inequalities, and therefore we are able to show that this function is indeed theta of n squared. All right, I think we have taken enough examples how to find the three constants that will allow us to show that a certain function is theta of another function.